So what we want to do next is called the standard normal distribution. You might be wondering, why do we need to bother? You will see the application later. You know, in the past, during the normal, when we were doing normal, the word normal now I have to be careful to use it. The probabilities of maybe events, or maybe if you, I think in particular, very recently, we talked about comparing spread and center of a distribution, and we use that to explain something. Maybe something like, how many more, maybe talking about, if this is about maybe score, in which subject the student passed more, something like that. Then we look at the mean and look at the one with the greater mean or greater standard deviation. Am I making sense? The standard normal distribution can help us to actually do comparison better, in the sense that regardless of what the distribution looks like, when the Z transformation is performed, everything looks the same. So it's like everybody is balanced. You will see in a bit. Remember that for a normal distribution, what is the probability density function? Anyone? Remember?
For the
probability density function for a normal, if X is a normal distribution with mean of that and standard deviation of sigma, then the probability density function f of x is, yes, does anybody remember the function? 1 over, no.
1 over h.
The probability density function, the function, not probability that x lies between a range. The function f of x itself. Listen, there's a difference between the function f of x and the probability that maybe x lies between 1 and maybe some a and b. So probability that x lies between a and b will be the integral of that f of x. This f of x is the probability density function.
It's the one.
Does that make sense? So for a normal distribution, what is the probability density function?
Isn't it 1 over h?
1 over, yes?
H?
No.
H. I was doing an investigation.
Try. Something 2, yes, I know. Before square root, there is something.
Standard
Sigma root 2 what? 2 pi exponential negative minus 1 over 2, okay, 1 over 2, no square root for now. Yes. X minus, no, mu divided by sigma all squared. I know it's not easy because you are not required to remember anyway, so you probably didn't really take note. Now, listen. If we let our z be x minus this over sigma, we can transform, this is more or less a transformation of the variable. Okay? This transformation of the variable is called the z transformation. And what happens to our mu and sigma if every x is converted using this? Again, your normal probability, your normal distribution is x, assuming a certain value of x. These are called the x scores. Okay? Now, for these x scores, we have a mean and a standard deviation, which we can calculate. Using this mean and standard deviation, we can transform all these scores into z scores. Does that make sense? This z score, we will see now that it also forms a normal distribution, and that is called the standard normal distribution. Why is this important? You will see in a bit. Now, everyone, consider this z score. Bring out the calculator. I will use the demo to show you what the histogram will look like. But I need you to calculate the mean and standard deviation of the x-scores that you're looking at. Quickly, please.
No, lo posee. Un lo sé. Un lo sé. Un lo sé. Say go.
Yes. Okay.
Vámonos.
No, we can't do that. He's gonna show.
So we have 1.
Vámonos.
Let me know when you get the mean.
4.
You got the mean as 4? Okay. So the mean is 4.
아마 저거 참.
And the standard deviation is what?
1.46.
Is it continuation?
Yeah.
Uh-oh, 1.48 something. Okay. We'll probably need to have an approximate value. All right. Maybe we can use a frequency table. Or do you prefer to do 1-1? It's not so many, actually. So what I want you to do now is let's convert each one of them. So basically, this is x minus the mean, which is 4, divided by 1.4, blah, 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 whatever that is. Am I making sense? So the next question is want to calculate the z score for each of them. So can you tell me with the first one what it will be? So I write all this, you tell me what it is. I need focus, please. There are 3 in 1, 2. Okay, 4, 1, 2, 4 in 5 places. And 5 in 3 places. Yeah, anyone? First one? Negative?
You want fraction?
No, because this is approximation anyway.
Wait, oh, no, it's 1.4.
1.4, like this?
No, sorry, no.
Negative
Come
2.1.
on, just substitute.
Negative. No, wait.
No.
2.1.
So let's use 4 decimal places, okay? I hope you use answer.
You can't.
If you can, you can't, right?
Yeah.
Okay, never mind. Just use 1.48 something. So tell me the first one, maybe to 2 or 3 decimal places is fine.
Negative 2.018.
2.018. Okay, so for 2, what will it be?
Negative 1.345.
3, 4,
5.
5. Okay. For 3, check for 3.
Negative 0.673.
Negative 0.673. Okay. Continue.
Or it's just 0.
Oh, so this is, I put it in the wrong place.
4 is just 0.
Say that again?
For 4, it's just 0.
4.
0.
0. Yeah, that makes sense. 5.
Positive 0.673.
Positive
673.
0.673. Are you sure? Oh yeah, makes sense. Then 6. 1.345.
Yes. Positive.
Yeah, positive.
You wrote it in 5.
Oh, I wrote it in 5. Okay. 1.345, and this should be 2.018 again.
Yes.
Confirm, please.
Yes.
Okay. So, can you find the mean and standard deviation of this now? So, don't forget, there are 2 of this. There are 4 of this. 1, 2, 3, 4, 5. There are 5 of this. There are 4 of this. There are 2 of this and 1 of that. I need focus, please. If you're not pressing calculator, don't disturb those pressing the calculator. Thank you. So let's see what happens to the mean of the z-score and the standard deviation of the z-score. we probably won't get the exact. So please double check as well. So I put how many they are, the frequency are here. Don't ignore the zeros. What do you get?
Yeah.
What's your mean?
Good enough, good job, man.
One variable.
The mean is 0. Yes, you're right. The mean is 0. You're right.
High wall.
And the standard deviation?
High wall.
1.
That's nasty.
Is it exact 1 or 1 point something? 1.0 something. So it's 1. This is what I was expecting you to get. And this shouldn't be, listen, this should not be a surprise to us. How do we calculate mean normally? In any distribution, mean is equivalent to what?
All of that. Sum of all of that.
No, not in terms of all that. Say that again? The expected value. Mean is the expected value, isn't it? So look at this. Mean of z is simply the expected value of z. Yes? Now z is transformed by that. So that is the expected value of x, right? Minus mu divided by sigma. Is that not? So this is simply expected value of, okay, this is x minus sigma, mu minus sigma. Right? So this is simply 1 over sigma, expectation of x, correct? Minus mu over sigma. What is expectation of x?
Expectation of x.
Say that again, speak louder please. I can't hear you. What is expectation of x?
Near.
Mu. Why are some people being quiet? For the random variable x, this is the mean. We're trying to find the mean of the new random variable z, which is a transformation of the random variable x. Am I making sense, please? So what do you notice about this? 0. That's what we are saying. Again, how do we find the variance of random variable z, which is automatically the variance of x minus mu over sigma? Remember, what is the variance of ax plus b? Yes? A squared variance of x. So a is that coefficient. B does not appear. Right? So as a result, the variance of z, this can be broken into the variance of 1 over sigma x minus mu over sigma. Am I right?
Yeah.
So what is our a in this case?
1 over sigma.
So basically this is going to be 1 over sigma squared variance of what? X. Now what is variance of x?
It's expected.
Sigma squared. Don't think too much. Just sigma squared. Right? And what does this mean? 1. So that's exactly what you have demonstrated. Okay? Now, this is why it is so important. Well, I think there is something here. There's a demo here. Your z-score and your normal, I don't want to use the word normal. So I call it x-score and z-score. Okay? Before transformation and after transformation, look at their Instagram. You can generate random numbers each time. It is approximately what? Normal. Can you see? Each time. And each time, look at your mean. and standard deviation for the Z, you see? Z especially. Regardless of what the mean of the normal distribution of the odd normal one is. Okay, let's change this. Maybe I put this as mean of 3 and standard deviation of 2 and generate different things. What do you notice about this one? It's still 0, 1, 0, 1 each time. Can you see? 0, 1, 0, 1 each time. Regardless. Okay? And you will notice, as long as this is the normal, this is also going to be a normal distribution. Now, why is this important? Let's say, for example, okay. Please look up. The paper is right in front of you. You are comparing two distributions. You want to know which is more spread, or you want to compare the center. Regardless of what the x-score is, this is what the z-score will look like. The mean is going to be 0, and the standard deviation is always 1. So you brought your distribution x, you brought your distribution y, you brought your distribution a. Different means, different standard deviation. This diagram will be different. So maybe your mean is 4, your mean is 7, your mean is 12. It might be difficult sometimes to compare in some cases, especially the spread. But in any case, everybody will have this z-score. Then you can see which is more spread. Am I making sense now? Okay? You can always look at the distribution in a more, let me say, in a form that can be easily compared. Because like everybody has the same, what is it called now? Yeah, you have the same borderline relative to a particular point. Then you can see different probabilities, you can make different conclusions, and so on and so forth. Okay? Now, one of the things that makes this cool is this comment here. It is easy to find, let's say, to interpret some values using z-score. If z-score of a number x, remember x is that value that is taken by that random variable. It could be, in this case, it is continuous, of course, because you don't talk about z-score unless you are dealing with a normal distribution, which it means you are dealing with a continuous random variable. Am I making sense? So the value that x takes, you always talk about how many standard deviation above the mean, standard deviation above the mean. In this case, you don't have to talk about 3 standard deviation above the mean anymore, because standard deviation is 1. So rather, it is simply standard deviation x above the mean. It's like, oh, 2 standard deviation above the mean. That's just what the z-score talks about directly. As you can see in this picture, this value 0. So in this value 1 is just saying 1 standard deviation above the mean. Unlike here, if I give you a 37 here, you need to know the mean to know how many standard deviation above the mean. Do you understand? But here, directly, you can tell us, oh, this is 3 standard deviation above the mean because you are dealing with a standard normal distribution. Okay? So quickly, the last one. Let's look at this comparison, this example that compares two distributions. And in the last, say, 5 minutes, there are some examples that I want you to do.
Probabilities from a normal distribution.
Okay, so
If we want to compare, so far we have seen how to find probabilities from a normal distribution. If we want to compare two normally distributed populations with different means and standard deviations, we cannot use probabilities alone. To do this, we need to use z-scores. The z-score of a measurement is the number of standard deviations the measurement is from the mean. It comes from a transformation of the variable we are studying to the standard or z distribution. The z-score for any value x is calculated using the formula x minus the mean all over the standard deviation. If a population is normally distributed, its z-scores will be normally distributed with mean 0 and standard deviation 1. Comparing the z-scores of two different distributions is only reasonable if both distributions are approximately normal. In this example, we want to compare a student's results for history and mathematics. If we assume the class results for each subject are normally distributed, we can compare the students' results by calculating their z-score for each class. In history, the students scored 73%, the class mean was 68%, and the standard deviation was 10.2%. We substitute these values into the z-score formula. Their z-score for history is about 0.490. In mathematics, the students scored 66%, the class mean was 62%, and the standard deviation was 6.8%. We substitute these values into the z-score formula. Their z-score for mathematics is about 0.588. In mathematics, the student's result was 0.588 standard deviations above the mean, but in history, the student's result was only 0.490 standard deviations above the mean. So, the student's result in mathematics was better compared with the rest of the class, even though the result was lower.
Does that make sense? So this is exactly what the comparison is about. Because it is easier, like I said earlier, that your z-score is, you don't need to know what is the mean anymore, because your mean is 0. So that value you are dealing with in the z-score is automatically how many standard deviation above the mean. Does that make sense? And you can see a very easy way to apply it here. Somebody scored this, somebody scored that. How would you know which is better? Oh, how would you know which is the strength of that student? Does that make sense? But by bringing, converting this to z-score, it is easier because the baseline for all z-score is 0. Okay? But in this case, it is not 0 for in the x-scores. It's not 0. You have to then deal with, the mean, above it, below it, and something like that. Okay, so this is what the comparison is about. Now, I have given you a paper. There is no time. I will have loved you to do this. Okay, but I'll send you the screenshot. Please try it. It's an application of what you have seen. Now, this is how we can use z-score to calculate probability. So please listen attentively. Please listen. If x is normally distributed with mean mu and standard deviation sigma, we have concluded, I've written some notes here for you. It's also from the book and some maybe 1 or 2 points added. Then z is also normally distributed with mean 0 and standard deviation 1. You see, this was not converted to 1, even though we know 1 square is 1. This is how you write a normal distribution to show that a random variable is normally distributed. Does that make sense? So please don't try to write 9, just leave it as 3 square. It is so that we can easily pick the standard deviation as 3. Okay? For any x1, x2, if x1 is less than x2, it is expected that z1 should be less than z2. Does that make sense? And you have seen that in that comparison. Because otherwise, there's no basis for comparison. If the proportion of x cannot be compared to that of y. Okay? So look at what we just did in the previous example. The two scores were converted to z-score, and the higher one was said to be higher. Okay, what that implies is that if x1 is less than x2, we expect z1 to also be less than z2 by extension. Okay, and as a result, if you want to find the probability that your number is greater than x1, it is as good as probability that z is also greater than z1. Does that make sense? And vice versa, if you have less as well. So you see, these are the two. The only difference is this is mu and this is 0. Understand? And if it is range, I'm not sure they put that. Yes, they did. If it is range between x1 and x2, it's as good as calculating between z1 and z2 as well. Okay, and here is an example. Using the technology, of course, we don't need to play this. So you want to find this probability, all you have to do is in your calculator, your mean is 0 and your standard deviation is 1. Okay? Because in your calculator you're going to need to supply the mean and standard deviation anyway, right? Your calculator will pretend you are dealing with X, but you know you are dealing with Z-score. Am I making sense? Similarly here, okay, just as we did before, 1 raised to power 99 and so on and so forth. Okay, I'll send you this screenshot if you need. So this is what I've given you, number 1. Can I ask everyone to look at that worksheet? Oh, this is what we just did actually. I didn't even know it's an exercise. I should have given you as an exercise. Can I ask you to do this? If you have the paper with you. So the probability curve is already given. The normal curve is already given. It's also on WeChat for you. So you can use the soft copy to write on your iPad. Use the diagram to calculate these probabilities. The first one is easy because it's labeled. But if you look at question 4, which is on the second page, that you need to think very well. So can I ask you to do 1AB, then move to question 4, and try to do maybe A and L, the last 2 in question 4, just for class practice. The first 2 and the first and the last in number 4, quickly. You will need calculator for question 4. We have like 2 minutes, so I give you just 60 seconds to quickly do that. Then I can demonstrate question 3 for you here. I've seen some past question that looks like question 3, so we had better just take one together as a class. You have business next, right?
Yes. Oh, we have a test today, so you might need to leave.
You have a test today?
Yeah.
Okay, so everybody stop. Since the business student have a test today, stop. I just explained this. You can actually do that later, please. So this question says, question 3 on the board. Okay, I'll send you the maybe worksheet later. Okay, this question says, given that X is normally distributed with that mean and standard deviation, and Z is that, so they are telling you this is the Z score for those corresponding X scores. Okay, now the question is, find A and B such that this happens. If this happens, it shows that the Z score for this is this, and the Z score for this is this. That's what that's what that means. So you go to from Z score is X score minus this over that. Am I making sense? This Z score will have been A if you substitute this. Can you see that? This is the X that you would have substituted to calculate and get this. Understand? So if you open the bracket, you're just going to get minus sigma, right? Over sigma. And so A is minus 1. Does that make sense?
Yes.
Then for B, if you want to get B, you would have applied the same, of course, maybe I don't need to, from this also, from the z-score is always the x-score minus the mean of the x distribution. Am I making sense? Divided by the standard deviation of the x distribution.